Hello everybody, my name is Johannes Lauer from Here Technologies. In this presentation I want to provide you an overview on the road roughness use case, which is part of the Automat project. The project is funded by the European Union within the Horizon 2020 Research and Innovation Program. Good quality of roads is a major concern for all users and maintainers of public infrastructure. Road damages, like potholes, do not only decrease driving comfort, but also heavily reduce safety for all drivers as well as passengers. With road roughness, we classify road as being good, fair, or poor, which is an additional layer on top of our map. Bad roadways cause an increased fuel consumption of vehicles and hereby led to more emissions. The American Society of Civil Engineers reported in 2013 costs of $324 a year for vehicle-related maintenance due to bad road quality. The National Transportation Research Group published in the Urban Roads Report that 1/3 of the US major urban roads rated in substandard or poor condition, providing motorists and truckers with a rough ride and increasing the costs of operating a vehicle. These facts show the importance of the availability of an updated digital representation of the road roughness that enables drivers to adjust their driving behavior and maintainers to improve the road conditions. Multiple industries are affected by road condition measurement. For example, governments are enabled to effectively budget and apply for maintenance funds, prioritize maintenance activities, and deploy resources. Automotive industries can develop suspension systems using a base pavement profile in navigation systems to enable better driving experience. Insurance companies can develop usage-based insurance ratings. Large fleet vehicles, which are most impacted by bad roads, can route with optimized fuel economy. And light fleets are able to further optimize delivery routes. So what is the current situation? We as Here Technology build our road roughness map from data collected by our Here TrueCars. The road network is segmented into good, fair, and poor classifications. Each segment has an average IRI measure computed by algorithms using the raw measures of the high precise inertial measuring unit of our Here TrueCars. A timestamp of when the reading was taken is an additional attribute stored for each segment. So basically, it can identify poor pavement and locate sudden change in elevation on the road, such as dip and bump. What is missing now in this road roughness product? Although we are able to provide data which is better and fresher as current available data, the fleet of our more than 100 Here TrueCars is not able to collect all the changing conditions on all the roads. Furthermore, the Here TrueDrives will only record a single lane of the road, which results in missing road roughness values for multi-lane roads. So, what if we could take the information of all of the available cars that drive day by day the roads of each and every country to calculate and update the road roughness product? Within the Automat project, we are able to access automotive sensor data from 3 OEM stakeholders, Fiat, Renault and VW. These vehicles are providing their data via the OEM cloud to a common vehicle information model, which is then connected to the Automat Vehicle Sensor Data Marketplace. With our HERE client software, we are accessing this data and computing updated road roughness measures using a machine learning model. To collect the ground truth data and to calibrate the machine learning model, we attached our HERE TrueCars with VW car data loggers. With this setup, we are able to collect automotive sensor data in parallel with the high precise IMU measurements of our HERE cars. This enables us to measure the road conditions with two independent sensor systems. One low-cost sensor system, which is available in almost every new car, and a high precise HERE TrueCar IMU, which collects the raw data for the HERE road roughness product. To calculate a model for every OEM, we are using our existing HERE road roughness product, which is also available for the 3 countries where the Automat OEM stakeholders Fiat, Renault and VW are doing their test drives. To update our road roughness data, our software consists of 3 consecutive steps: the training data preparation pipeline, the learning pipeline, and the prediction pipeline. The data preparation pipeline pulls the data from the cloud storage via the CVIM data model, pre-processes all data, all signals, labels the data with the HERE Route Matcher API, and stores the outcoming data in different formats. The labeled data is then used to generate correlation plots. This is a basic technique for visual analytics of the collected data. This enables us to select sensor measures that are strongly correlated with the road roughness measure. It also identifies dimensions and measures which generate a bias on the road roughness measures. With this information, we are generating a learning pipeline to compute a model for the feature classification. As input data, we are using the labeled sensors from all of the OEMs, extracting a larger set of features by computing statistical values and moving window measures, as well as taking the raw measurements. This will be then the basis for the supervised machine learning process. During the fitting model process, we are calculating a best fitting model for our input data. The result of the learning pipeline is then a fitted model as well as a model score which represents the model precision. As an example, we are calculating the model score for the data collected by our HERE TrueCars. This dataset consists of 180,000 observations and 436 features, for example acceleration, velocity, and their moving window measures. The statistics within the table show a very accurate training dataset and a stable model. The mean accuracy of this model is roughly 65%. This model is then be used as an input for the prediction pipeline. The Automat Marketplace provides the vehicle sensor measures in the CVIM data model. Within the prediction pipeline, we pre-process the data, which consists of several data cleaning processes. We are extracting the features, which means increasing the vector space, and using the fitted model to predict the road roughness. With this, we are able to predict the road roughness with an accuracy of the underlying fitted road roughness model. Let's take a look on the newly classified OEM datasets. In the left figure, we are seeing our road roughness product on top of the HERE base map. The points in the foreground are representing the latest sensor measures recorded by a Fiat car, uploaded to the cloud storage and accessible via the Automat marketplace. The formerly generated model is then used to classify the fresh incoming data. The differences between the measures and our road roughness product could be a result of road maintenance within the last year, changing road conditions, or model inaccuracies. In the right figure, we are seeing a nearly perfectly classified road, which means the detected road roughness category is equal to the previously high precisely computed road roughness data from the HERE TrueCar IMU measures. On this slide, we are showing a further example for another OEM where we predicted road roughness categories by using vehicle sensor data from a VW Passat during a drive in March 9th, 2018. In the figure, we could see the equality and the discrepancies compared to our road roughness model, which consists of data that is nearly 2 years old. These two examples show that the computation of road roughness measures using the Automat marketplace is possible and is able to increase the freshness of our road roughness product. I would like to thank the whole consortium for the fruitful discussions and the collaborative work within the Automat project. I would like to thank my colleagues at HERE who contributed to this project, and I would like to thank the European Union for supporting these activities within the Horizon 2020 Research and Innovation Framework. And last but not least, thank you for your attention.